In the last video, we defined resistance and talked about resistors. In this video, I'd like to turn my attention to thinking about what goes into designing a resistor, at least a bit. So to that end, I'm going to present you with a series of thought experiments. So here's my first thought experiment. Let's say I've got a fairly thick piece of material like this, so a large cross-sectional area, and another piece of material like so that has a smaller cross-sectional area, A2. And let's say, despite my art, that both of these are the same length. Which one of these would you think would have the greater resistance? Choice number 1 or choice number 2? Pause the video and get back with me. Yeah, it's going to be choice number 2. This will be the harder one. This will be the higher resistance device. Simply because since it's thinner, it's going to be harder to shove electrons through it, just like it's harder to shove water through a skinny pipe than a fat pipe. Okay, let's go ahead and do our next thought experiment here. So in this case, both of the materials have the same cross-sectional area. Oops. But in this case, so they both have area A. But in this case, we'll say the length of object number 1 is longer than object number 2. Which one of these is going to have the higher resistance? Go ahead, pause the video, get back with me. Yeah, in this case, it's going to be object number 1. The resistance is going to be higher here, simply because it's a longer pipe that we're going through. So just like you have more viscous drag with a longer pipe when water's flowing through it, same kind of idea here. All right, one more thought experiment. So in this case, we'll go ahead and say they're both the same cross-sectional area and they're both the same length. In fact, I am just going to do bring that down there. I'm just going to do a copy-paste. There we go. So they are definitely the same cross-sectional area, the same length. The difference is what I'm making these out of. So let's say this one is ceramic and this one is copper. Which one do you think is going to have the higher resistance here? Yeah, it's going to be the ceramic. Ceramic's an insulator, for crying out loud. You really have to work at it to get any kind of charge to flow through that. Copper, on the other hand, being a coinage metal, is a really good conductor. So what we get out of this is that the skinnier you are, there seems to be an inverse relationship to cross-sectional area. The skinnier something is, the higher the resistance. There's a direct relationship with length. So that's good. So the longer the device is, the higher the resistance. And also the choice of materials comes into play. All right. So if you combine all of that together, what we end up saying is that the resistance of our The resistance of our device is rho L over A, where rho is the resistivity. So that thing that looks like a funky P, it's not. It's our friend rho that we've seen before. But just again, a quick reminder, if we use the special paper from 2nd grade, it's basically like you draw a tadpole and then you resist with all of your might the urge to draw a little face on it. Okay, so this is the resistivity. So now if we go and play with the units here, we know that we need to get ohms out over here. This is meters, that's meters squared. So this whole fraction here is going to be units of 1 over meters. So whatever this is, I have to times, it has to be such that if I times it by 1 over meters, I end up with ohms. And so it turns out that the units of resistivity are ohm meters. And this is material dependent, and you can find the values in tables. So as an example, let's go with the wire that you use to make a toaster out of. It's a special alloy of nickel and chromium called nichrome. So let's say that I have a 10-meter long nichrome wire. And let's say it has a diameter of 0.1 millimeters. What's the resistance of this wire? All right, so I'm going to have to look up the resistivity of nichrome. You can find that in tables. And depending on the exact alloy, it'll fluctuate a bit, but a decent number is going to be 1.5 times 10 to the negative 6 ohm meters. Okay, so then my resistance is going to be rho L over A. This will be rho L. Then the area of a circle is pi d squared over 4, where d is the diameter. So I can rearrange that to get 4 rho L over pi d squared. All right, so we can go ahead and plug in here. This will be 1.5 times 10 to the negative 6 ohm meters. We said that the nichrome wire is 10 meters long over pi. And then I said it was 0.1 millimeters in diameter, so that's 0.0001 meters in diameter squared. If you grind that through, you get 1,910 ohms, which is a perfectly respectable value for a resistor. Remember that typical values for resistive devices run anywhere from about 1/10 of an ohm to about 100 million ohms. Okay, I'm going to finish this out with one other thought, which we'll do more with later, but I kind of need to introduce it now for some stuff. So I'm going to finish off by introducing Kirchhoff's junction law. Kirchhoff, junction law. He will also have a loop law that we'll run into later. And if you're wondering, is this the same Kirchhoff as in Kirchhoff's 3 laws of spectroscopy from astronomy? Yeah, it's the same guy. He got around. So this turns out to be a direct analog to the equation of continuity when dealing with incompressible fluids. So the idea is, let's say I've got some, beast of a conductor, and I've soldered a joint together like so. I got some horrendous thing that looks like this, for instance. We'll say 3 amps flowing in here, 6 amps flowing out there, 2 amps flowing in out there, 4 amps flowing in here, and we want to know what's going on over here. So the way I like to express Kirchhoff's junction law is to say charge in equals charge out. Charge or else charge piles up until it does. So what this means is, in steady state, if I add up all the currents flowing into some junction, like for instance this junction right here, the sum of all the currents flowing into it has to equal the sum of all the currents flowing out of it. Now, for the first 10 billionth of a second or so after you throw the switch, You may actually have a momentary imbalance while charges are shifting around in the junction to sculpt the electric fields through the junction to then get you to a point where the current, sum of the currents in equals the sum of the currents out. Again, this is a process that takes less than a 10 billionth of a second typically, so we pretty much ignore that and just say that whenever I have a junction, I can add all the inbound currents together. In this case, I got 3 plus 4 equals 7. I can add all the outbound currents I know about so far. That's 2 plus 6 equals 8. So in order to get it to balance, I conclude that my mystery current has to be 1 amp into the junction. All right, so we will be revisiting this along with introducing Kirchhoff's loop law later on, but I thought this was as good a place to introduce it as any. Alrighty, I'll catch you in the next one.